Hi all, my name is Tommaso Cucinotto from the Real-Time System Laboratory of Scuola Superiore Sant'Anna, and I'm going to present an experiment in which I show how to provide temporal isolation among concurrent running virtual machines by using the real-time scheduler we developed in context of the IRMOS European project, Interactive Real-Time Multimedia Applications on Service-Oriented Infrastructures. Basically, the problem that we face with is the following. Whenever we deploy multiple virtual machines on the same host, the virtual machines of course compete for accessing the shared resources available on the machine. First of all, they compete for accessing the CPU, and this is especially true when deploying multiple virtual machines on the same core, which may be needed for better consolidation of service. Now, the problem is that these virtual machines will try to fight one against each other in order to get access to the CPU, and this basically will result in a performance of each individual virtual machine that is not predictable, is not stable, and this leads of course to problems whenever considering the business rules and business models behind deployment of virtual machines in a cloud computing infrastructure, and considering the service level agreement that may be in place between the platform providers and the customers. So what we do here is to apply real-time scheduling technologies at the CPU level in order to guarantee a sufficient level of isolation between the performance of independent virtual machines. What we want to achieve is to have a performance of each application that is only dependent on the workload of that very application and not on what else is running on the system, disturbing the operations of each single application. So let's see what we can do here. Here we are logged onto one of the servers which we are running our real-time scheduler. This is basically a modification at the kernel level of the scheduling strategy of Linux, scheduling of processes. This way we can basically encapsulate each virtual machine deployed on this host with a temporal capsule, which is basically a CPU share allocated to the virtual machine, but with a fine control over the time granularity over which the CPU is guaranteed. So in this case we are providing to the first virtual machine 30% of the CPU by basically ensuring the virtual machine runs for 60 milliseconds every 200 milliseconds. For the second virtual machine we have a similar situation. We are ensuring we are granting a 40% of this core share by basically allocating 80 milliseconds every 200 milliseconds. Here the periods may be heterogeneous among the virtual machines, and they mainly depend on the requirements of the virtual machines themselves. So let's see what happens here. We deploy in this system two virtual machines with an e-learning scenario provided by Junti Labs. And in this scenario we have basically a server residing inside the virtual machine, and we have a client which runs here from this virtualized Windows instance from a laptop. And in this client basically we are emulating the behavior of 10 users which move around a given GPS location, and these users will continuously submit requests to the server requesting for information about the contents available in the neighbor of their position. So this way the users are updated on in real time about the contents available around them, and they can stream their contents over their mobile phones. And this is of course a simulator of users, but the application works also with the real client running on real mobile phones. So now what can we do here? Okay, we can exploit this graphical user interface for monitoring the situation, and now we start the first batch of clients So we start 10 users. Here the users progressively log into the server. Then we have 10 users moving randomly in the area, and depending on how they move and their actual emulated GPS positions, these users basically submit a dynamic workload on the first virtual machine here. And as we can see, we are getting an average delay in serving requests coming from these 10 users, which is basically fluctuating between 15 and 30 milliseconds, more or less. Okay, so now what we can do is, what we can ask ourselves is, okay, what happens if I deploy a second virtual machines on the system? Now basically we can start. This virtual machine is already deployed. However, we can start the real workload on this virtual machine by simulating 40 users concurrently accessing the virtual machine. And what we get now is that, as you can see, the users progressively log into the server, and so the average delay of this virtual machine at last achieves a values again in the range between 10, 15 and 20, 25 milliseconds. Now, as you can see, starting this workload on the second virtual machine did not impact too much the response times, the average response times as experienced by users of the first virtual machines. This is exactly what service provider should ideally provide to customers, a stable performance of virtual machines. We can highlight even more the temporal isolation effect by simulating the startup of a third virtual machine that is executing a boot operation. The boot operation is a very CPU intensive operation for a virtual machine, so we start this virtual machine by providing it with a minimum level of resources. Okay, and as we can see, we can contain the behavior, the temporal behavior of this third virtual machine by not allowing it to disrupt the performance of the other two already deployed machines. In fact, the performance of the other two machines basically remains the same. Now, what is interesting is, let's see what happens if we disable the real-time scheduling of IRMOS. So let's disable it. Okay, now the virtual machines are being scheduled by standard Linux scheduling policy. What happens is basically that the third virtual machine, which is a very CPU intensive activity, manages to take up as much as 60% of the CPU, and the other two virtual machines are getting so much less than before, so they're suffering, and their performance basically is completely determined now by is completely subverted as compared to the previous performance that we were getting beforehand. Now basically the Linux scheduler provides us with no control about how to actually, what exact performance to provide to each virtual machine that is deployed on this system, because the Linux scheduler is trying here to achieve a kind of fairness property among the virtual machines, but it actually depends on how much time each one of them is active as compared to the sleeping times. So, and this is resulting in the third virtual machine taking a lot of resources here. Now we can enable real time again, and now we have again our temporal capsules that allow to contain the interference of the last CPU intensive activity on the system, and at the same time to keep the performance of the other two virtual machines according to what we had foreseen at design or benchmarking time for this system. So summarizing, by using the IRMOS real-time scheduler developed by the Scuola Superiore Sant'Anna and specifically by the Real-Time System Laboratory in the context of the IRMOS project, it is possible to isolate temporally the performance of dependent virtual machines deployed over the same physical host, and specifically the same CPU core, by making it in such a way that the performance experienced by each virtual machine is basically dependent on mostly the workload of the virtual machine itself, and not on what other virtual machines are actually present and doing over the same system. This is also another interesting experiment we made, in which we show also on the x-axis what is the CPU share of the one virtual machine, and on the y-axis what is the average response time of the same virtual machine. And the various curves here are obtained at various CPU shares of the second interfering virtual machine. As we can see, under the use of the real-time scheduler, the response times are only slightly increased as compared to what happens when the second virtual machine, the disturbing virtual machine, is idle, which is the curve highlighted here with which is the curve, the bottommost curve here. And so basically we have a good deal of isolation between the two virtual machines. So thanks for your attention. In case you need more attention, feel free to visit the IRMOS project website, which is this one, and also my personal homepage, which is this one, where you can find all the information about what I said here.